Now let's talk about different types of data and the probability distributions that we use for these different types of data. This is really important because archaeologists and forensic anthropologists, we always encounter a lot of different types of data, and depending on the type of data that you're working with, you could end up using very different statistical approaches and tests to kind of analyze those data. And so when it comes time to classify your data so you can figure out what type of statistical analysis to run, I think that there's kind of two key factors to consider. The first of these is whether your data are continuous or whether they are discrete. Continuous data are, for example, data that can be decimals, 1.75, 2.34, things like this, where you can have any value in a certain range. Those would be continuous data. In contrast, discrete data cannot necessarily take on any value within a range. Count data, for example, 0, 1, 2, 3, 4, these are discrete data because when you're, for example, counting the number of sites in a given area, you can't really have 2.45 archaeological sites. That wouldn't really make much sense. You either have 2 sites or you have 3 sites. So anything like this where you can't really take decimal places, that could be discrete data. Another example of discrete data would be presence or absence data, yes or no's, zeros and ones, where it can either be a 0 or it can be a 1, a no or a yes, an absence or a presence. These types of data are also discrete. Now, in addition to just being continuous or discrete, it's also important to ask whether your data are bounded or unbounded. This is kind of the other important consideration in determining what sorts of statistical analyses to run. If, for example, your data can range across any value from negative infinity to positive infinity, they are unbounded. Right? If it can be both positive and negative is kind of a general shortcut to this. You're dealing with unbounded data, or at least data that's close enough to being unbounded that you could conceptualize it as unbounded. In contrast, though, bounded data might be something that can't be negative. Right? If you're measuring the length of a humerus, you can't have a humerus that is negative 35 centimeters long. That wouldn't make any sense. That's not realistic. Linear measurements like that are only positive, and so it's bounded by 0 in that case. You can have measurements conceptually going up to infinity, but positive infinity, not negative. This would be one example of a bounded type of data. Data that are between 0 and 1, or just 0 and 1, are also bounded. If you're looking at proportions or percentages, which are just proportions multiplied by 100, proportions are bounded because you cannot necessarily, in most cases, have a proportion of 1 point something. It's either 0 point something up to 1. So I prefer this classification system of continuous versus discrete and bounded versus unbounded. And this is becoming a far more common and kind of popular way to understand data. But there is an older system that some of you might have encountered where data were grouped into these different types of whether they were interval, ratio, ordinal, or nominal. These terms, I think, are more confusing and a little bit less clear about what exactly they mean. I think it's a lot easier to understand continuous and discrete and bounded and unbounded than it is to remember the difference between interval and ratio data, for example. But some of you have probably encountered these terms before, and so I just wanted to highlight for those of you who have that interval data would be equivalent to continuous and unbounded data, while ratio data would be continuous and bounded. Ordinal data would be discrete and most likely bounded, while nominal data are simply discrete and different categories of data with no order to them. Out of these terms, I think that ordinal is the only one that I regularly use. I don't really describe data as being interval or ratio, but I will describe data as being ordinal when there is a rank order to the data. When you've got these different discrete groups or categories, that there is an order to them. And so if you haven't heard these kind of terms before, interval and ratio, don't learn them now. It's really not worthwhile in most cases. Just learn continuous and discrete and bounded and unbounded. But if you are familiar with these other kind of typological terms, know that it does map on to this continuous, discrete, and bounded versus unbounded typology as well. Now, just as examples, I want to work through a couple types of data that archaeologists and forensic anthropologists can encounter and kind of unpack how we could describe these on this kind of typology that we just discussed. So if you're looking at a site and you're counting debitage, you're counting kind of the waste products of a lithic reduction process. You've got all these different pieces of stone, and you're counting them. What type of data is that? Well, because you're counting things, and you can't really have 1.7 pieces of debitage. You either have one piece or you have two pieces. I would say that debitage counts are discrete. They're integers, and so like all integer data, they are discrete. I would also say that debitage counts are bounded. Right? You can't have -7 pieces of debitage unless you're doing some weird calculation, perhaps. But in terms of a simple raw count, you can't have a negative value, so it's bounded by 0. So debitage counts, I would say, are discrete and bounded by 0. What about the breadth of a distal tibia? You're measuring a skeleton's distal tibia and how kind of wide that end portion is. Well, it's a measurement, a linear measurement, and so linear measurements can take decimal places, right? You can have a distal tibia that's 5.3 centimeters. That would make perfect sense, and so it seems to be continuous data. But a measurement can't be negative, right? You can't have a distal tibia that is -7 centimeters in breadth. That wouldn't make any sense. And so these data would be bounded by 0 as well. They're continuous, but bounded by 0. The proportion of a certain pottery type by layer, right? If you count up all of the chord-marked pottery and divide it by the total number of different kinds of pottery in a certain layer in an archaeological site, that proportion value is going to range between 0 and 1. In this case, it would be continuous. You could have a value of 0.3792, but it's bounded by 0 and also bounded by 1. And so this type of data would be continuous but bounded. And of course, we could actually model it as discrete and bounded if we kind of conceptualized the simple whether a piece of pottery is chord marked or not as a 0 or 1. This is a common way to understand proportions as well. What about the thickness of a sunflower seed coat, right? That outer layer of a sunflower seed. Well, it's a linear measurement. All right, so it can't be negative. You can't have a seed coat that's negative 0.3 millimeters or something. It has to be a positive value, so it's bounded by 1. But it is continuous. It can take a decimal place. So we've got continuous and bounded by 0. What about the presence or absence of a fused epiphysis? All right, if we're looking at a skeletal population and trying to see how old individuals are, for example, and we're looking at the distal femur, trying to see whether or not these epiphyses are fused to the rest of the bone or not. If it is, you could mark that as a 1. If it isn't, that's a 0. So in this case, you've got all 0s and 1s. Those data would then not be continuous. Those are discrete data. It's a 0 or it's a 1. And those data are also bounded by 0 and 1. You can't have anything below 0 or anything greater than 1. So in this case, we've got discrete and bounded data. What about the latitude of archaeological sites? Right? If you're comparing the latitude of different sites, what type of data would that be? Well, latitude, right, can range from 0 at the equator to 90 degrees north, or from 0 to 90 degrees south. Now, the way that this is often kind of described, these types of data are often described, is that if you've got a northing latitude, that's a positive value, and if your latitude is south of the equator, it's a negative value. So positive 20 degrees latitude would be 20 degrees north, and negative 20 degrees latitude would be 20 degrees south. This is also the same with longitude. along that east-west axis. East is positive, west is negative. And so in this case, we can take continuous values here. The latitude could be 20.37. That would be able to make perfect sense. And technically, latitude and longitude are bounded, right? You can't have a latitude value of greater than 90 or less than negative 90. But in a general sense, we can kind of treat these data as unbounded because they take positive and negative values. So even though they are realistically bounded, they often behave like unbounded data. So this is a bit of a gray area, but officially speaking, these would be bounded and continuous. But with a little bit of stretching, we could say that this is kind of unbounded data. What about the proportion of gazelles in a series of assemblages? Right, a proportion, right, continuous, ranging from 0 to 1, so it's continuous data, and bounded by 0 and 1. And finally, what about the number of different types of bifaces? Right? Again, it's a count, so these are discrete. You can't have 1.7 bifaces. It's one biface or it's two bifaces. And counts cannot be negative, so we've got discrete data that are bounded by 0 in this case. This is just a bunch of different examples to help you kind of think about your data and to illustrate to you how this typological system for classifying your data works. Now, I want to talk next about the normal distribution, or the Gaussian distribution, because all of these different types of data can, in many cases, best be approximated using certain probability distributions. The Gaussian, or normal distribution, is perhaps the most common of these probability distributions. The normal distribution takes values which are continuous and unbounded. Right? So decimal places and can be both positive and negative on either side of 0. That's what a normal distribution handles. All these probability distributions have different parameters. The normal distribution has two parameters. There's the mean and the standard deviation. The mean is how the normal distribution approximates the central tendency of the distribution, kind of that meaty part of the bell curve in the middle there. And the standard deviation is a measure of dispersion, of kind of the variation in values around that central tendency. Now, what can we actually use a normal distribution for, right? I said this is perhaps the most common type of probability distribution, and if any of you have taken statistics classes in the past, I guarantee you that most of the time you spent in that statistics class was spent thinking about normal distributions and data which are normally distributed. But let's go back to that previous slide and think about these 8 different examples. Are any of these actually going to be normally distributed? Debitage counts, breadth measurements, proportions, thicknesses, presence or absence. In fact, I think the only one in this entire slide that you could model using a normal distribution and be kind of very technically accurate in doing so would be the latitude of sites, right? Even as we discussed, latitude is technically bounded, but because it can be both negative and positive, you can begin to sort of approximate a normal distribution in that sense. And so I think that if you're going to use a normal distribution here, it wouldn't really be perfectly appropriate for any of these data except for perhaps the latitude of sites. And so even though the normal distribution is kind of the most commonly known distribution, it's not actually all that useful for a lot of real-world data that we encounter. There's arguments to be made against this, however. One of these is based on what's known as the central limit theorem. And this is the idea that when you have variables and you sum them together, the sum of those variables often tends towards a normal distribution, even if the variables themselves are not actually normally distributed. So with a little bit of manipulation and in certain other statistical contexts, a normal distribution is quite appropriate. So this is why it's kind of a foundational and fundamental and very important distribution to be familiar with. And also kind of the reason that it's taught. But the reason that it's taught so frequently is also because it's quite simple mathematically, as opposed to a lot of other distributions that are a little bit more complex. But before talking about other distributions, I also do want to mention this idea of a z-score. Now, a z-score is simply a measure of distance from the central tendency of a normal distribution. So it's basically the number of standard deviations away from the mean that a certain value is. Right? If you go one standard deviation away from the mean, right, that's a z-score of 1. 2 standard deviations away is a z-score of 2. And this term z is used for normal distributions. Other different types of distributions have other kind of terms, right? If you're looking at an F distribution, you're talking about an F score. Chi-square distribution has a chi-square score. A T distribution has a T score. I mentioned these 4 because whenever we're running some statistical tests and models later on, you'll encounter F scores, chi-squared, T scores. And just know that this is kind of similar to a z-score and that it's a measure of distance from the central tendency of that probability distribution. It's kind of telling you how far from the mean or whatever other metric of central tendency you're using a certain value is. And so a Gaussian or a normal distribution, as I said, is perhaps the most commonly taught type of distribution, and it takes continuous and unbounded data. Right? There are 3 other types of probability distributions that we're going to discuss in this course. There are, of course, many others out there, but we're going to focus in on just 4 of them, the first of which is a Gaussian distribution, the second of which is called a log normal distribution. In a log normal distribution, the data that it can take are continuous. It can be decimal places, but they're bounded by 0. That's what separates it from a straight-up normal or Gaussian distribution. Now, you can only have positive values, so this is a good distribution to model measurements, for example, where you can have only positive data but continuous. Another type of distribution that we'll deal with is called the binomial distribution. This is, formally speaking, a discrete distribution that is bounded by 0 and 1. So when you're talking about presence-absence data, yes, no values, anything that can be coded as a 0 or a 1, this could be a binomial distribution. Again, useful for those presence-absence data, but also with a little bit of manipulation can be useful for proportions or percentages. And finally, the 4th type of distribution that we're going to talk about is the Poisson distribution. This is a discrete distribution that is bounded by 0. So at first glance, it might seem kind of similar to a log normal distribution, but a log normal distribution is continuous, where you can have a value of 20.37, for example. In a Poisson distribution, you can't have decimal places. This is a distribution of integers only. So it's only values of 0, 1, 2, 3, 4, 5. Count data is the most common thing that a Poisson distribution is used for in archaeology. And of course, because it's a count, it's not often negative, and so this is a distribution that is bounded by 0. Now, it's also important to note that not all of these distributions and the others that exist out there use mean and standard deviation. Really, each of these probability distributions has their own parameters, some just one parameter, some several. And each probability distribution is tailored to specific types of data. Here I'm giving you a very simplified understanding of these 4 distributions. The real definitions are actually far more technical and complicated. But if you just understand the basics of it, that's enough of a foundation to begin using them and then to investigate them further on your own. And as I've said, there are many more probability distributions beyond just these 4. These are just the basic ones that we're going to cover here, but there are tons of others: the beta distribution, negative binomial, gamma, Dirichlet, Bernoulli, tons of others out there. If you understand kind of the basics of using these, though, you can then begin to investigate those on your own and hopefully understand what you're reading about a little bit better.